Okay, let's start. So before I start the lecture about data challenge, I believe you have received the email for data challenge. You have access to in-class Kaggle. Data challenge is an individual task, so only the final project is group-based. For data challenge, you have to do the challenge individually. So the task is a task of dimensionality reduction. We cast it as a classification because it's pretty hard to estimate the quality of data visualization because it's unsupervised learning. In all unsupervised learning cases, we don't have good measures actually to see the quality of the output. Clustering and data visualization are cases of dimensionality reduction that we can't evaluate it in a fair way. So we cast the problem as a classification problem, but problem in essence is a dimensionality reduction problem. So we fixed the classifier. So the classifier is 5 nearest neighbor classifier. You are not allowed to change the classifier. You can't use any other classifier. So the classifier is fixed, 5 nearest neighbor classifier. What you need to do is to apply the techniques of dimensionality reduction to basically extract informative features from the data set and then pass those features to a 5 nearest neighbor classifier and then upload your result to Kaggle. So Kaggle automatically rank you, and you can see your position in class, and you can see your score. But in terms of mark, you're not competing with each other. It's not that the first rank get the full mark and the second rank get less than. It's not like that. So we know what the best answer is. If you pass the threshold of the best answer, definitely, I mean, threshold would be a little bit even less than the best possible answer. But if you pass the threshold, you're going to get the full mark. And basically, your mark will be evaluated based on how close you are to the threshold. So maybe all of you get the full mark, even if you are not the first rank according to the Kaggle, you know. So you are not competing with each other in terms of mark. Is there any question about data challenge?
So will we have to build our own nearest neighbor algorithm, or can we use a already existing?
You can use a built-in function for k-nearest neighbor classifier. So any language that you use has a built-in function for k-nearest neighbor and can use that one. I mean, MATLAB has, Python has. So you can use a built-in function. In data challenge, basically, you can use any built-in function.
Okay.
You can do anything that you want.
Okay. And the same thing for the PCA, or the dimensionality reduction?
Yes, for dimensionality reduction, you don't need to build it yourself. You can use existing code for any method in dimensionality reduction. Any other question? Yes?
So do we have to use MATLAB?
Sorry?
Do we have to use MATLAB?
You can use anything that you want. It's up to you. But you have to submit your code at the end, you know. So we would like to check that if your code produced the result that you are claiming. But you can use any language, any built-in function. Okay? Any other question? You can't use built-in function for assignments. For data challenge, you can. Okay, so in the last lecture, we learned about isomap, and we learned that basically isomap is multidimensional scaling when you change Euclidean distance to geodesic distance. And then we started talking about locally linear embedding, LLE. And we learned that LLE has 3 steps. In the first step of LLE, we construct a k-nearest neighbor graph. And K would be a parameter to LLE. So you have to choose how many neighbors you're choosing. The condition is that your graph needs to be connected. So means from any point, you need to have a path to any other point. So I think at the end of the last lecture, I said fully connected. It's not, I mean, technically it's not correct, because fully connected means a point is connected to all other points. What I meant was that it needs to be connected. I mean, you can't have two separated parts in the graph. So if K is too small, you may have a disconnected graph, may have different parts. That's LLE is not going to work in that case. So you have to make sure that K is large enough that makes your graph connected. And it shouldn't be too large, because we saw some slides that if it's too large, then it approaches to linear methods. If it's connected to all other points, then the locality actually cannot be estimated as a linear patch. It has a curvature on it. The estimation is not a good estimation. So that's the first step. The second step of LLE was to minimize for all points, you want to know each point, how each point can be reconstructed by its k nearest neighbor, and you optimize this objective function and you find weights. And we learned how to do this in the previous lecture. The third step of LLE is to minimize this objective function. So from solving this objective function, we know the reconstruction coefficient of each point. We fix them, so we have those points. So what I want to do is to find a representation for y such that in this representation is in lower dimensional space. X was in D, y is in P. In lower dimensional space, I want to have a representation of points such that each point can be reconstructed by its k nearest neighbor with exactly the same set of weights. So basically, locally, we preserve the geometry of the data by preserving the weights that each point used to be reconstructed. Okay? So we know how to solve this one. Let's just see how we can handle the second objective function. Okay, y was a P by N matrix of N data points. So let me define y column I to be only, or let me start from here. Okay, I define I to be N by N matrix, identity matrix. Then I define I to be one column of I. So basically, it is 0 everywhere except in the position I. So it's one of the columns of identity matrix. Okay? So that's 1 at position I and 0 otherwise. Okay, also I define an n by n matrix W. And here basically I put, for any points, I put all other weights according to that point. For only k nearest neighbor of a point, we do have weights, and there are zeros for any points that is not among the k nearest neighbor. So I can define a column of W as n by 1 vector such that it is 0 everywhere except W1 to WK. So basically W1 to WK are weights of k nearest neighbor of xi. And 0 otherwise. Okay? So having these notations, I try to rewrite this cost function in a form that it does, it's based on just matrices and vectors. So I want to get rid of this summation. So, I have yi here. Yi using these notations can be written as yi, right? Basically, if I take the whole matrix y and multiply by this vector, it just pick the ith column of I. Everything else would be knocked down. So yi is yi. Okay? So what about sigma wij yi? How can I write this using these notations? I need basically, I have y, and I have to add up only k of them and use some coefficients that I have for point I. So if this summation if this is a reconstruction of xi, so basically you can write it as this matrix multiplication. See, this is a vector, n by 1. This is p by n. This p by n times this matrix. You multiply any point which is not involved in the reconstruction by 0, and the points that are involved in the reconstruction by its corresponding coefficient. Okay? So having this, the objective function would be, basically I need to minimize I equal 1 to n of yi, which is capital yi, minus this summation, which is y wi. Okay. I can also get rid of this summation here, because this is summation of this norm. Means I have to do it for every single column of this matrix. So simply I can put the whole matrix inside of this norm. So I can write it as yi minus yw. squared. Because this is norm, by definition of norm, it is the summation of all columns of this matrix. And this is only one of the columns of this matrix. So I can just get rid of the summation and put the whole matrix inside the norm. Right? Is that clear? Okay. So we know that Frobenius norm can be replaced by trace. We can write Frobenius norm in terms of trace. So it's minimization of y, trace of this matrix transpose times itself, right? Before I turn it to trace, let me write it this way. And then I will turn it to trace. So it's trace of this matrix transpose, which is I minus W transpose Y transpose times the matrix. Okay. Does it make sense so far? Yes.
The summation here on the second whiteboard, is it over J or I?
Which one?
The last one on the second board.
Here?
It's not yeah, this board, the last summation.
This is over J.
And that's YI or YJ?
Sorry? This is YJ. Sorry. Yep. This is over J. This is YJ. Yeah, thanks. So this is trace, basically. You know, since it's trace, I can rotate elements of the trace. So I have basically I minus W transpose Y, I minus W. So I can put this I minus W here. And then I can put this Y here, right? So this is basically trace of Y, I minus W, I minus W transpose, Y transpose. So that's what I want to minimize. This is noun. Identity is noun. W is the set of weights that I computed in the first step. So this is noun. Let me call it M. I want to minimize trace of Y, M, Y transpose. Okay? So it's pretty similar to many optimization problems that we had before. What would be the solution to this problem? Sorry? Would be 0, right. Without any constraint, this would be 0. So, but LLE do the optimization subject to some constraint. There is a constraint here for the first objective function that summation of Wij is 1. And there's a constraint, and actually there are two constraints here. And one constraint is that Y transpose is identity. In fact, if you want to be exact, it's exactly the same as the original paper. It's 1 over n Y transpose equal to identity. And there's another objective that summation of Yi is 0. Means the mean of projection is 0. Okay? For I equal to 1 to n. Okay, without any constraint, the solution of this is 0. But let me add one of these constraints. Y transpose is identity. Or 1 over n, Y transpose is identity. It doesn't change the solution except by a scale. So what's the solution to this optimization problem now? We had similar problem. If you just write the Lagrangian take derivative, you can see that it's pretty similar to this problem that we had in PCA, for example. But this is a very classical problem, and it appears in many places. In general, if you want to maximize trace of Y transpose M, Y, subject to the constraint that Y transpose Y is identity, if you want to maximize it, the solution would be the maximum eigenvectors of M. If you want to minimize it, the solution would be minimum eigenvectors of M. Okay? These are pretty classical problems in terms of trace optimization. And if you have any doubt, you can just write Lagrangian take derivative. Okay? So the solution for this, since we want to minimize it, is bottom eigenvectors of M. Okay? So I want Y to be p-dimensional. So how many eigenvectors should I pick? P, right? I have to pick, it seems that I need to pick p eigenvectors, the bottom p eigenvectors. But in fact, you need to take p plus 1 eigenvectors, because always the first eigenvalue of this matrix is 0. And corresponding eigenvector for that 0 eigenvalue is a constant vector, is a vector of 1, 1, 1, 1. Okay? So M always has one eigenvalue equal to 0. That's the smallest eigenvalue. It doesn't have any negative eigenvalue because it's positive semi-definite. So the smallest eigenvalue is always 0. And always it has one eigenvalue equal to 0. So eigenvector corresponding to this eigenvalue is 1, 1, 1, 1, 1. So it's not useful. We're going to ignore this one. So ignore the eigenvector corresponding to 0 eigenvalue. Then pick well, let me write it this way. Pick the first bottom, the first the p plus 1 first bottom eigen vectors, and then ignore the 1 that's so basically you need to pick the first, the bottom p plus 1 eigenvectors. The first one, the first eigenvalue is 0. And corresponding eigenvector is 1, 1, 1. Just ignore that one. And look at eigenvector 2 to p plus 1. Basically, the solution would be eigenvector 2 to p plus 1. So don't forget that y is p by n. Rows of y, not columns of y. Rows of y are these eigenvectors. So rows of y or columns of y transpose are eigenvectors 2 to p plus 1. Okay? Yes?
Can you explain why, again, why that m is equal to 1 over n y transpose?
Why m is equal to what?
The equation of 1 over
No, it's not equal to this. This is the constraint. That's the constraint of the problem. M is equal to I minus W times I minus W transpose. Then we add a constraint to the problem because if it's unconstrained, the solution is 0. Y equal to 0 is the optimum value.
why is one eigenvalue 0?
Always there is one eigenvalue equal to 0. We see the reason for that in the rest of this lecture. If you are familiar with the concept of Laplacian of a graph, I minus W is Laplacian of this graph that you made. Because, Laplacian of a graph is basically D minus W. So if you represent your data as an undirected weighted graph, if this W represent the weights of the vertices of the graph, then D is a diagonal matrix such that each element on the diagonal is a summation of a row of W. That's actually what's happening here. W is a weight on the graph. Summation of W on a row is always 1 because of the constraint that we had before. So this D in this case would be identity. So identity minus W is Laplacian of the graph. One of the properties of Laplacian is the number of 0 eigenvalues of a Laplacian shows the number of components that you have in a graph. So if a graph is connected, there is 1 0 eigenvalue in the Laplacian of the graph. If graph has 2 parts, then there is 2 0 eigenvalues. If it has 10 parts, then there is 10 0 eigenvalue, and so on. So since we need to have a connected graph, then there is always a 0 eigenvalue because it's Laplacian. It's Laplacian squared, actually. Yes? So we'll see that because the rest of the lecture is about the spectral clustering, which works with Laplacian, and we'll talk about.
So those that don't know what Laplacian graph is,
Well, I can't teach like graph theory here, but just I will introduce. I will write the definition of Laplacian in more details. Yep.
Can you explain why the rows of y are eigenvectors 2 to p plus 1?
Why the rows of?
Why the rows of y are the eigenvectors?
In this classical problem that I wrote on the, in the classical problem that I wrote on the board, we had trace y transpose my. The solution for this is eigenvectors, and eigenvectors would be columns of y transpose. Here, actually, you have, instead of y transpose y, you have y transpose. It doesn't matter. The eigenvectors would be just rows of this or columns of this. If you have y transpose y, that would be the other way around. M is n by n. The eigenvectors are n-dimensional. But y is p by n, right? So eigenvectors cannot be columns of y because they're n-dimensional columns of y are p-dimensional. They're rows of y. But if you want to see this exactly, just write the Lagrangian, take derivative. You will see that the solution, I mean, there are going to be columns. I mean, eigenvectors will be appears as columns of y transpose, which are rows of y. Yes?
How do you make through the second constraint?
Good question. What happened to this second constraint? That's actually a question in your second assignment. But it has to do with this zero eigenvalue. The fact that this matrix has a zero eigenvalue and a constant eigenvector satisfy this condition. But you will see that in your assignment. Yes, both constraints are satisfied. But if you just solve the problem with this constraint, the second constraint already is satisfied. You don't need to include it in your optimization. Okay, any other question? Yes. Sorry? Here? You know, I mean that M is an n by n matrix. You decompose it. You see n eigenvectors. You ignore the first eigenvector. You know, you have n eigenvectors. You ignore the first one because you see that it's constant. It's 1, 1, 1, 1, 1. You take the second eigenvector, put it as a row of y. The third one, the fourth one, the fifth one, and then if you have chosen 5 of them, this is going to be 4 by n matrix, because these are n-dimensional, and that's your y. Okay. Any other question? Yes.
Do you by chance order the eigenvectors by the size?
Sorry?
Do you by chance order the eigenvectors by size of the eigenvalues? So like
Yes. When I say the bottom eigenvectors, eigenvalues, I mean order them.
Okay.
From a small to large. The smallest one is 0 always. Then the second one is the second smallest one, which is a positive number because it doesn't have a negative value. Okay? Okay, so we know how to solve LLE now. So LLE is basically eigendecomposition of this matrix. So far, all methods for dimensionality reduction that we had was in the form of eigendecomposition. PCA was eigendecomposition of covariance matrix. And dual PCA was eigendecomposition of X transpose X. Kernel PCA was eigendecomposition of a kernel of X. MDS was eigendecomposition of X transpose X again. And LLE is eigendecomposition. Isomap was eigendecomposition of sort of kernel that we made out of geodesic distance, and this is eigendecomposition of this matrix. Yes?
Can you clarify one step? You see how you go from the bottom in y minus w squared?
Okay.
To the top row, the bottom one, going from there to up there. Yeah, what exactly happened?
So we had this before, that Frobenius norm of F is trace of A transpose A. That's exactly what happened. This is your A, trace of A transpose A. Mm-hmm. Oh. Okay. You tried this example in your assignment with PCA. That's the same example when we try LLE on this. You know, in terms of PCA, you saw that basically these different colors get mixed up because the underlying manifold is not linear. When you try PCA on that, these points will get mixed up with these points because PCA believe that this is a subspace, try to collapse everything on the subspace. But here you can see that points are not mixed up. You know, ideally, this manifold should be unfolded. You can see that LLE makes some distortion to basically the shape of this manifold. So we cannot trust this, the length of these axes in terms of the original manifold. And we had this constraint here. Basically, this constraint makes any rectangle square, you know, because on each direction, you're going to have the same variation eventually. So forget about length and forget about distortion, but you can't see any point here mixed up in terms of color. Yes?
You know it's distorted because it didn't unravel it flatly and there's still like a curve in it?
Yeah. Yes, yeah. But if I change the number of points here, sorry, the number of Ks here, you know, here I had 2,000 points and K here is 30, right? If I say K is equal to, I don't know, 150, it's going to be a slow, but with large number of neighbors, as I said, it approaches to PCA, so we are starting to consider a large portion of the manifold as a patch, which when this patch is not linear anymore. So here, just look at the points here. You know, all of these colors are mixed up. You know, blue and yellow are mixed up here. Yes?
So with kernel PCA, we had a reconstruction issue because we couldn't represent phi of x. Do we have the same reconstruction issue here?
Yeah, we can't reconstruct points using LLE. We can't reconstruct point using isomer. We have another issue here, actually, that we didn't have in kernel PCA, out of sample problem. So if I show you a point that was not among the endpoints that you observed, you don't have any direct way to map it to low-dimensional space because you have to go through the whole process again. You know, everything is based on this decomposition of M, which is n by n. Now I have point n plus 1, which I haven't observed before. What should I do with this? There is no direct and exact solution to this. There are approximations, but not exact solution. Okay. So that was for a large K. If I choose K to be very small, then the graph is not the graph is not connected anymore, and this is, you know, the result. You know, it doesn't make any sense. Okay. So that was LLE. This is isomap. Isomap is quite slow. So I should have changed 2000 point to like 1000 point because it takes time. But isomap also does a pretty decent job in this case. And you don't see, points being mixed up. So it means that it has been unfolded. So we'll wait for the result of this. Meanwhile, I can start a new topic. So our next topic is spectral clustering. It's not dimensionality reduction, it's a clustering method. We get back to dimensionality reduction again, but I introduced spectral clustering first because it has a very close connection to a dimensionality reduction method called, okay, here is the result. In terms of distortion, it's way better than LLE. And you don't see points getting mixed up here, so it has been unfolded nicely, but it's slow. So this topic is a spectral clustering, and a spectral clustering has close connection to a method in dimensionality reduction which is called Laplacian eigenmap. So that's why I start with this clustering method now. And we'll see the connection of a spectral clustering with a Laplacian eigenmap. And we'll get back to dimensionality reduction again. And then in the second part of the course, you will learn about clustering in more details. But since clustering is since a spectral clustering is a clustering method, let me start with this example. If I ask you to cluster these objects in two clusters, how do you do that? Yes?
You could do it one of two ways. You could do black together and red together, or in circles and squares, but those seem like evenly.
True. You can put blacks in one cluster and reds in another cluster, or you can put squares in one cluster and circles in another cluster. Can we argue that one of these solutions is correct and the other one is wrong? No. I mean, if I just ask you to put it in two clusters, you can't argue that one of them is correct, one of them is wrong. So clustering by itself is ill-defined problem due to some of the issues like this. You don't know what the correct underlying solution is. That's different from classification, that you know what the correct answer is supposed to be. You can compare it with that. But here we don't know what the correct answer is, actually. It depends on how do you see these objects, from which perspective, which features are important for you. And theoretically, actually, there is a classical paper which proves impossibility of clustering. So it introduced a couple of axioms, which seems quite trivial, aspects that you want to have in any clustering method. In any clustering method, if you have a data, if you reduce the distance inside each cluster and increase the distance between points in two clusters, still you have to have the same clustering, right? If I reduce the distance between these objects in each cluster and take them apart, still I have 2 clusters. If I multiply every distances by a constant, still I need to have the same set of clusters. You know, there are a couple of axioms that seems to be quite trivial and intuitive, and you want them to be in any clustering method. And then proof goes to show that it's impossible to satisfy all of these axioms at a time. So any clustering method is going to violate some of these axioms. And basically this paper proves that if these intuitions, if your intuition about clustering is important to you, intuitively you think that clustering should behave this way, then it's impossible to cluster any data. It's impossible to have an algorithm to cluster any data. But those theoretical results aside, we do have many clustering algorithms, and definitely each of these algorithms are going to violate some of those axioms. But it doesn't matter, you know. Still, you know, violating some of those axioms, you know, it does a job, but this job, basically there's no guarantee to say that it's a correct answer to this problem compared to result of any other cluster. For some, based on some features that are important to us or based on some aspects that are important to us, we're going to evaluate that this clustering is better than the other one or not. Okay, spectral clustering is not the first algorithm in clustering that should be discussed in a course about clustering, because it's a pretty advanced method compared to many common clustering techniques like k-means clustering that we use every day, people use every day. It's way better technique for clustering compared to k-means, and we will see k-means later on. But as I said, due to the connection of these two Laplacian eigenmap, I introduced this first. Okay, this is the setting of the problem. Suppose that I have n data point. So given n data points, and then I have a notion of similarity. You know, it's based on distance or whatever. I measure the similarity of points. So given n data points and notion of similarity, we construct a graph. So I construct a graph G. This graph is weighted and it's undirected. So V here actually is set of vertices and E is set of nodes. These vertices are weighted because it's a weighted graph. And weight on each vertex shows the similarity between two nodes that basically make that vertex. Okay? So any endpoints that you give me, I measure the similarity between points, and then I construct an undirected weighted graph. Now suppose that I want to, yes?
You mean the set of edges?
Yes, I mean, sorry, V is set of edges. And the E is set of nodes.
Don't you mean the other way around? E is edges?
No, These are nodes.
I just mean because V stands for vertices, and a node is a vertex.
E stands for edge.
Okay, so it depends how you define it, right? You want to define it the other way around? It doesn't matter.
I just mean that's the typical.
Yeah, okay. Okay. Happy? Yes. Okay, it doesn't matter actually. You know that we define it that way. You can define it. Yeah, but yeah, I use vertices wrongly. Yeah, nodes and edges. True. And there is a weight here, which shows the similarity between points. Okay? Okay, I have this graph, and I want to cut this graph to two parts. You know, I have a graph, and this graph how can I cut this graph to two parts? Well, I want points or nodes in one subgraph to be similar to each other, and nodes on the other subgraph be similar to each other. Okay? So suppose the graph is connected. If the graph is connected, to cut it to two parts, I have to cut some of the edges. Okay? I have to cut some of the edges, but I have to choose which subset of edges needs to be cut to make it two graphs such that graphs in each part are similar to each other. You know, one way to approach this is to choose basically set of edges such that the weights, the summation of weights on those set of edges are small. Because weights shows the similarity between points, right? I want to disconnect this graph, and I'm going to remove those edges which shows a small similarity between points. When they are small means they are very dissimilar. So basically, I want to differentiate points in terms of their dissimilarity. When their similarity is small, means they are very dissimilar. So I have to cut edges that are, the weights on those edges are small. Does it make sense? Okay. So this is actually a problem, a classical problem in graph theory. So I can define notion of cut. Cut of A and A bar is summation of Wij, and W is the weight of each edge, such that I comes from set A and J comes from set A bar, and A bar is basically a set of nodes here minus A. Yes?
Would you say the weights represent the distance between points? Like the larger the weight, the larger the distance?
You can do that, but in this case, you have to go for the larger summation of Wij, if it's distance. So that's similarity, so similarity should be, yeah.
Is the graph fully connected?
No.
How do we make the graph in the first place?
K-nearest neighbor graph, for example.
Just some way to make it.
Could be fully connected graph, but doesn't need to be. Any graph. The only requirement here that we have is it's a connected graph. Yes? A is a subset of V. You know, V is A union A. Or so you have some nodes. A subset of nodes goes to one set A. The rest of nodes go to A bar. Okay. So basically, if you agree with the intuition that I share with you, I need to minimize cut, or I need to minimize summation of Wij when I comes from one set and j comes from the other one. Okay? So we have to try to solve this, but there is a problem with this intuition that we had so far, and the problem is that it can lead to a solution which makes a very unbalanced A and A bar. You know, in an extreme case, suppose that I have a data like this. So it seems that this point should be in one cluster, this point should be in another cluster. But if you just go with the intuition that we had, since this point is outlier, is pretty far from any other point, the weight on this one would be quite small because it's very dissimilar to other points. Distance is large, so similarity is small. So if you want to minimize this cut function, the optimal solution would be to cut just this one and decide that, okay, this single point is in one set A and the rest are in A bar, for example. So if your task is clustering, basically this optimization doesn't lead to a good clustering because it can result in a very unbalanced cluster. Yes?
Intuitively, though, if we were only considering there to be like two clusters, then wouldn't the one really far away from the rest of the data seem the most different? Like, it would need its own cluster, so that would be like a good solution in terms of like the intuition?
No, this could be outlier, you know. You have some measurements about some phenomena and your device doesn't work correctly, and you have a measurement which is pretty far from the distribution of the rest of the data, but your algorithm is going to pick this one against the rest, right? So your algorithm needs to be robust in terms of outliers. And usually in clustering and classification, we always have sort of implicit assumption about the number of points in each cluster, in each class. We want them to be balanced. In some applications, it's not a good assumption, you know. In some assumption, you do drug discovery, you know, the drug is the number of molecules that have this property is way, way smaller than the rest. So it is really unbalanced. But in usual applications, usually we have an implicit assumption or explicit assumption about number of points in each class or cluster to be almost the same. So we want to avoid this. And to avoid this, we're going to change this cut to something which is called ratio cut. And ratio cut is basically cut A bar divided by the number of points in A. So this is cardinality of set A, the number of points in set A, plus cut A bar A divided by A bar. So cut A bar and cut A bar A are the same, you know. Just you divide cut by the number of points in set A, divide cut by the number of points in set A bar by the cardinality, and add them up. So it avoids the case that 1 point is in one cluster, because it makes one of these ratio quite large, right? If you want to minimize this summation, then the optimal solution happens when both of them are small, but not one of them is very large. Okay, so we would like to minimize the ratio cut. So basically now our task is to find points in two clusters or set of edges in a way that ratio cut is small. Okay. Okay. Now I define a vector f, which is n by 1. And then I define fi, one element of this vector, to be each element of vector A, F, I define it this way. The number of points in set A bar divided by the number of points in set A, a square root, if I comes from set A. And A divided by A bar, the number of points, with a negative sign if I comes from A bar set. This is like labels, right? Points in A, I'm going to label them positive. Points in set A bar, I'm going to label them negative. But just not +1, -1. It has a value always. If the number of points in set A and A bar are the same, it's going to be +1, -1. But if here I have 100 points, here I have only 50 points, then it's 100 divided by 50, a square root positive, or 500 divided by 100, a square root negative. Okay, was a question here? Okay, so it's just labels. I'm just defining this. I'm defining F this way. Okay, now I claim that minimizing Wij Fi minus Fj squared is equivalent to minimizing ratio cut. So that's my claim. I claim that if you define F this way, then minimizing this objective function over all I and j is equivalent to minimizing ratio cut. Yes? What do you mean that f of I should be equal to f of j?
Depends on A, which is the same as the
I is index, right? I would say for point xi, fi is defined this way. If point xi belongs to set A, that's the label of that point. If point xi belongs to A bar, that's the label of that point. We don't know xi is in set A or in set A bar now. But end of the day, if it turned out that x is in set A, the label corresponding to that point is this. Otherwise, it's this. Yes?
Is there an efficient algorithm for minimizing this? Because I remember there isn't one for minimum cut problem in ground theory.
So that's what we want to do. Yeah, it's NP-hard problem. I mean, there is no efficient, but we can relax the exact solution and come up with some efficient solution for it. That's what we want to do. Okay. So that's my claim. Okay, let's prove this claim. If I write this objective function, wij fi minus fj squared over all I and j's, I can write it as two parts. If I is from set A and j is from set A bar, then this is wij times, then fi, because I comes from set A, is A bar over A minus the second part, which is A over A bar squared. Plus another term. If I is in set A bar, but j is in set A, then this is wij. Then this is I is in set A bar, so it's negative. A over A bar, negative A bar over A squared. Right? I had this summation over all I and j's. There are two cases. Either I comes from set A and j comes from set A bar, or I comes from A bar and j comes from A. Okay? So I split this cost function to two cases. In the case that I is from A and j from A bar, then fi has this value, fj has this value. In the other case, that I comes from A bar, but j comes from A, then this is I, this is j. Okay? Okay, now I have I from A, j from A bar, wij. So if I expand this square, then the first term is A bar over A. This is going to be A over A bar. And then I have 2 times the first term multiplied by second term. What this term is going to be?
1
Or 2?
or 2, sorry.
Yes. 2 times this is going to be 2, because this times this is going to be 1. So plus 2 squared plus I is in A bar, j is in A, wij, the same thing will happen here. So it's A over A bar plus A bar over A plus 2. Sorry?
Isn't it not supposed to be there? Didn't you expand that just now?
Sorry, so what's your
Did you
question?
expand the square?
How did I expand this?
Did you do that?
Yeah.
So there shouldn't be squares in the last one.
Yes, sorry. Yeah, thanks. Yes. Okay. Is that clear? You know, this bracket, I can take it out of this summation. So it doesn't have anything to do with I and J. And yes.
So at this moment, is the set A and A bar decided, determined, or they are still unknown?
Sorry?
Because our objective is to divide the set B into A and A bar.
Okay.
But right now, the expression says you're taking I from A, J from A bar. So how do you decide, like?
No, we don't know which one from A. The only thing that I want to show that if you optimize this, it's the same as optimizing this. So I don't know which points comes from A, which points comes from A bar, because I haven't minimized the ratio cut yet. I haven't minimized this one yet. My claim is that if I do minimize this, this is going to happen. It's identical to minimizing ratio cut. Okay, so I can take these out and I can factor it, you know. Basically, I'm going to have like A bar over A plus A over A bar plus 2 times summation of Wij when I comes from A, J comes from A bar plus summation of Wij when I comes from A bar, J comes from A. Right? So what is this quantity here? It's cut, right? So this is cut. Cut A bar. This is also cut A bar A. And cut A bar and cut A bar A are the same. Okay, so this is basically 2 cut A bar. So what about this first term? You know, I have a 2 here. I can write this 2 this way. I write this 2 as A over A plus A bar over A bar. Then I add these 2 terms, which they have the same denominator, and these 2 that they have the same denominator. And here I have 2 cut A. So there's 2 here, and there's cut A bar here. So it's 2 A bar and this term plus A, and then I add these 2, A bar, A plus A bar, cut A bar. Okay, what is cardinality of A plus cardinality of A bar? N, right? Which is cardinality of V, which is N. So this is N. And this is N. So I factor this N. And I take it out. It's 2N 1 over A plus 1 over A bar cut A bar. Then I put this cut inside this. So it's cut A bar divided by A plus cut A bar, or A bar, A divided by A bar times 2N. So what is this quantity? It's ratio cut. Okay. So the claim is proved now. If I minimize this, it's equivalent to minimizing ratio cut, because this 2N has no effect in the minimum, right? So we decided to minimize ratio cut. Now we learned that instead of that, we can minimize this objective function. Now we have to see how we can do this, which would be the subject of next lecture, how to minimize this objective function. We don't know yet. Any question? Okay, see you next week.